All right, we want to take a look at the mean value theorem, but to get going on the mean value theorem, we need this thing called Rolle's theorem. Most calculus textbooks, the mean value theorem comes fairly early in the chapter on applications. One of the consequences of the mean value theorem is used in graphing, and that consequence is if the derivative of the function is positive, then the function is increasing. And if the derivative of the function is negative, then the function is decreasing. This is something that I always feel like I think the students can understand pretty easily without the mean value theorem. And to me, the mean value theorem is a first step towards integral calculus, calculus 2. And so I generally save it for the end to be just that ready, that last thing you do before stepping into Calc 2. It's the thing that gets you there. It's going to turn derivatives into antiderivatives and get us started on that process. So Rolle's theorem is where it comes from. Rolle's was a whole mathematician back in the times when calculus was first being discovered. He didn't actually agree with the way what calculus was doing, and he was trying to prove some different things. But anyway, the only thing he's remembered for is a thing in calculus. He did see the light later and decided that calculus was okay, but at the time he was trying to prove something else. But here's Rolle's theorem. If f is a continuous function on the closed interval from a to b, and f is differentiable on the open interval from a to b, at least, maybe the closed interval, but at least on the open interval, and f of a equals f of b, then there exists a c, a point c, on the interval ab, such that f prime of c equals 0. Let's take a look at the picture of this. What does this mean? Well, first of all, f of a and f of b have to be the same. Okay. Now, to say the function is continuous on that closed interval means it's continuous at every point along the interval, which means the limit as you go to each point is the same as the function value at the point, which essentially means I can draw the graph of it without picking my pencil up. To say it's differentiable means you don't have any vertical tangent lines, you don't have any sharp corners, you don't have any cusps, you don't have anything that goes crazy. There's a unique tangent line at every point. So it's smooth and it's connected here. So, what does it look like? I don't know. It looks like something. Who knows? But it has to start and end at the same elevation here, at that same height. That being the case, Rolle's theorem is stating that there has to be a point somewhere, at least one point here, C, where the slope of the tangent line is equal to 0. You got a horizontal tangent line right there. There may be more than one, but there's never less than one. There exists at least one place where the derivative is equal to 0. Okay, this is Rolle's theorem. Now, this isn't exactly what Rolle was proving, but this is the essence of what Rolle is proving. I'll talk about what he actually did later. But let's just do a quick proof here. The proof stems from the fact that we know that f is continuous on the closed interval, finite length interval from a to b. And back when we were doing optimization, we had the theorem that says if you've got a continuous function on a closed interval, it has to have a maximum and it has to have a minimum, right? Must be a max and a min, right? So if it has one of those, somewhere in the middle, if f of c is max or min in the open interval from a to b, right, then we also have a theorem that says any local extrema, max or min, for which the derivative exists, then the derivative has to be 0. Well, we said that f is differentiable everywhere on the interior. So if the derivative exists and you got a max or a min, then f prime of c is equal to 0. Okay, which is what we're looking for. Now there's a possibility that maybe you don't have a max or a min on the interior, but they both happen at the endpoints. if max and min happen at the endpoints, how many p's are in happen? I have no idea. Probably not 3. Happen at A and or B. Well, notice that f of A equals f of B. So if the max and the min both happen at the endpoints, then they both have to be the same. And so f of x equals f of A equals f of B for all x on the interval. On the interval from A to B. If the max and min happen at the endpoints and the endpoints have the same height, then everything's got to be at the same height. In which case, the function's a constant function, and f prime of x equals 0 everywhere. So if it's everywhere, then at least for one point in the middle, it's equal to 0, right? So Rolle's theorem. If you have a continuous function that's differentiable everywhere, and the endpoints have the same elevation here, f of A equals f of B, and there's got to be a point in the middle where the derivative is equal to 0. Okay. What Rolle was doing is he was trying to not use the notion of derivatives, but he had this. He'd start off with a polynomial, ax to the n plus. Well, let's just do like a cubic, right? So he had ax cubed plus bx squared plus cx plus d. And then he'd define this other polynomial, which he'd define this way as 3ax squared plus 2bx plus c. Is that 2b or not 2? No, it's 2b, okay. So he didn't call this the derivative. This was just this other polynomial. And what he proved was that if you had two places where this polynomial passed through the x-axis, then somewhere in between this polynomial passed through the x-axis. Well, I mean, you and I know that the graph of this polynomial is a cubic of some kind. Who knows, whatever it looks like, right? And somewhere in between here and there, you must have had a spot where the tangent line was horizontal, and so the derivative at this point is here. So this polynomial would, actually this polynomial looks like, something like this, right? Because it's showing you the slopes. The red one is showing you the slopes of the blue one, and you got positive slopes to 0 right here, negative slopes through here, back to 0, and then positive slopes on the end. And so, yeah, in between any two x-intercepts of this polynomial will be an x-intercept of that polynomial. Anyway, he proved that, and now we generalize it to what's called Rolle's theorem. Okay. And really our only use for Rolle's theorem is to prove the mean value theorem, and I will do that in the next video.